So for section 6.5, we turn our attention now to modeling with normal distributions. And we have a number of applications in the coming chapters that rely on us assuming that sample data can be modeled using normal distributions. We would call this property being the normality of sample data. So we assume that this random sample that we have in front of us is taken from identically distributed and independently normal distributions. In order to reasonably do that, though, then we have to have ways of assessing the normality of sample data. And we'll start with relatively easier and less rigorous ways to assess the normality of data. For instance, here in this video, we will be talking about fitting bell curves to sample histograms. So I have here a relative frequency distribution that is constructed from sample data collected in a batch of SAT scores according to the current scaling, which is the lowest score possible is a 400 and the highest is 1600. In order to appropriately create a relative frequency distribution, we had to make the last class, the 1600 class, a singleton. That is, they're only values that are exactly equal to 1600 count in this category. So here we have the relative frequencies, and remember that if we are talking about the connection between frequentist probability and the collection of sample data, what we're doing then here is we're actually creating an analog to a discrete probability distribution. So our task then is we're going to have the histogram corresponding to this sample data, where the classes are going to be distinguished by the lowest score in each one, and we have a class width of 200. So roughly speaking then, it'll look something like this. And I'm being relatively imprecise here, but we certainly could be more precise. Oops. So what I'm doing now is I'm constructing the frequency distribution, the histogram for this frequency distribution. And this will give us we'll be representing the sample data visually. Now, how do we fit a bell curve to this histogram? So remember that a bell curve necessarily is a density curve, where we need to be sure that we're mostly approximating the mean and the standard deviation. Now, if we had the exact mean and standard deviation, well, in this case, we'd be talking about if it's a sample, we would have the sample mean and the sample standard deviation. And we would use those to estimate the mean of the normal distribution and the standard deviation of that same normal distribution. So for the sake of illustration, we'll just assume that the mean is right here and that this is our bounds of the first standard deviation line on either side of the mean. So this will appear to look like, I hate when that happens. That's not great. Let's try that again. So it could be drawn better, but that is our fitted density curve. So this is x bar, this is x bar plus s, x bar minus s. And so this is not a very precise technique, but of course we need some key characteristics that will help us determine if a normal distribution is a so-called good fit. So one, is the histogram approximately symmetric? So on both sides of the mean, do we have bars of relatively same height? Is it vaguely bell curve shaped? One thing that's really important here is that a normal distribution, so the bell curve shape is sharper than we realize. So this would be a bell curve shape. But this, no, sorry. This wouldn't be, because that is just like a half, this looks vaguely like a half circle or like part of an arc. That wouldn't be it either. It also doesn't look like a triangle. So that also doesn't fit. So this is more of a triangular curve. And we would call this more like an elliptic curve. So not these two. Make sure it's bell-shaped. And two, we want the tails to be approximately the same length and shape. If one tail is significantly longer than the other, then that means we have a skew. And third, which is time-consuming but is possible to do, if we take a finer histogram with a finer class width, does that automatically lead to a better fit? If we have a very large data set, then it should. Otherwise, if we have very few data values, so if our sample size is small, then this won't be a helpful heuristic. And ultimately, this technique comes down to eyeballing it, which isn't super rigorous. So we'll have to explore a couple more techniques that will help us work with assessing normality of sample data.